the detection of a quasar started because they saw things that looked like stars, but using Hubble's law, they knew that they were much further away. So they could see the redshift in the star spectra, basically, or what they thought was initially a star. And the redshift indicated that it was much, much further away. It was going very fast away from us, as Hubble's law indicates. But they were coming up as little points like stars. Most galaxies that we see as little blobs. We can make out spiral structure. Ellipticals has some shape to them. So typically they're not stars, or they're easy to identify as something that's not a star if it's got some shape to it. But these objects were moving very far away, so instantly we knew that these things had to be very, they're moving fast away from us. We knew they had to be very far away. And we now know quasars, these quasi-stellar objects, we now know that they are very far away, very bright, active galactic nucleuses, or nuclei. We use the abbreviation AGN here, and so these are the core of galaxies, and they are very, very bright, and very far away typically. Now, it's not always the case. We'll look at some of them that are relatively close to us, but for the most part, we see quasars actually in the distant, the distant part of the universe. They're not all. Most of them aren't close. Now, we know that they are just the nucleus of a galaxy because if we look at a light curve, so what this is a plot of brightness over time. So each one of those lines there, if it's a little bit fuzzy, you're looking at a really small picture of this video, each one of those elements is 6 months apart. So each label on the bottom is talking about 6 months apart. And so this is a quasar called 3C66A. More precisely, it's a blazar. It's actually emitting in gamma rays as well. But this is a light curve. So over time, we see the emission goes up and down by about 2 full magnitudes. So this gets kind of close to almost about a 10 times difference in brightness. And so for an object that's already this extremely bright, that we're seeing these objects very far away, this can't be some galaxy size effect. Galaxies are hundreds of thousands of light years apart. So if it was one effect in the galaxy, it would take 100,000 years or more, whatever the size of the galaxy, basically, to make a change that would affect everybody or everything in that galaxy. It can't just be one effect that simultaneously affects the entire galaxy in some swell. So in order for us to estimate the sizes of these objects, we can see how quickly they vary. And these vary on the scale of months, or a couple of them on the scale of kind of years, where they have these effects. They get really, really bright for a small period of time being maybe months or years. And then they diminish in size, or diminish in brightness here. And this gives us a hint as to the size, or at least it sets an upper limit for how big it can be. So this particular quasar kind of gets brighter and dimmer on a kind of a 2 or 3 year time scale, and so we know that this object, or the structure that is here, can't be bigger than about 2 light years across, because if there's some material that comes in at one end of it, it's not going to not going to brighten the other end of it until in that whole time. So we know that it has to be less than this time kind of in distance, because nothing can go faster than the speed of light. So a year or 2 time variability indicates a light year or 2 maximum size. And so we know that these have to be relatively small objects, and we know now that they are just the nucleus of one of these galaxies, and we'll look at that here in just a second. Now, if we look at closer active galaxies, now we don't necessarily consider these guys quasars per se, but they are active galaxies that are near us, likely exhibiting some of the same effects that we would expect. So this is the elliptical galaxy M87, and the center of the galaxy is emitting this very large jet. So you can see that it's a very massive galaxy that makes up that glowing part in the upper left. And so this jet is being pushed out at extreme speeds, extreme energies, and is pushed away from the galaxy. And we see it in all sorts of wavelengths. And so we can study this and hopefully understand what's happening at the core of these active galaxies. And we now have seen pictures a little bit up close of some of these. So this is actually the looking right in the very center of M87. So M87 is that galaxy that I showed all the jets of. And if we look really close, it's close enough for us so we can actually resolve and make out actually what's happening in the very center. And so we know that there is this very fast spinning disk of stuff that's at the very core of this. And then we see on the right picture there, the little kind of glowy donut is actually the supermassive black hole at the core. So just like a black hole, rather than being a stellar mass black hole, of which they maybe have 5-10 solar masses worth of material in it, a supermassive black hole is at the center of galaxies and is millions or possibly even billions of solar masses. So that's 1,000,000 times the mass of our sun, up to 1,000,000,000 times the mass of our sun. These are incredibly large black holes, and they are kind of churning the material around them. They're spinning rather fast, or at least the material around them is spinning rather fast. And we see this glowing material in all sorts of wavelengths. And this is likely what's causing these quasars, is that you have these very massive objects, these supermassive black holes that are eating material. And material near them is heating up, and to the point where they become very bright, or maybe they end up emitting a jet out of the pole of the black hole. So the black hole itself is spinning, and so it'll emit a jet out of the kind of the top, the spinning axis of it, as a way to conserve angular momentum. So we get these extremely energetic jets that maybe are pointed at us even, and so we get some of the material kind of being thrown directly at us. Don't worry, it's really far away. They're not harmful to us really in any way. But much like we talked about with gamma ray bursts, how if they're aligned at us just right, sometimes they can look a little bit different. We get the extra brightness from a gamma ray burst. Now these are not gamma ray bursts, but they are kind of the same idea, where something is spinning and we get the material flying off the axis like that. Now, the history of quasars, we actually find that the number of quasars actually peaked a few billion years ago. And so this actually corresponds also to a peak in star formation rate. So one of the things that we can kind of grade galaxies on is what is their star formation rate? How many stars are made there per year or per time frame? And so we see that if we track the number of quasars, so we look how far away each of these quasars are. Remember, distance is going to give us a sense of time as well, because of the light that it takes to get to us. So things that are further away are older. And so as we see these this amount of quasars, we find that there is a correlation here between the number of quasars and the star formation history of the universe. So we can kind of connect these two, at least that there's something that either one is causing the other, or something is causing both of these things simultaneously. And so we think what is happening here is that quasars are likely colliding galaxies. So each of these galaxies would have a supermassive black hole in the center, and as they collide and as they interact, that creates a whole bunch of more food for the active galaxy, for that quasar at the center. So the quasar becomes exceptionally bright because of all the extra dust and gas, possibly stars that it's actually consuming, and just being merged into the black hole as a whole. But these structures are so extreme that they emit this incredible amount of light. Now, at the same time, the excess amount of dust and gas with the two galaxies colliding creates enough shocks, and there's enough extra material there to create extra stars. So is it one causes the other causes, they cause each other? I think it's likely that there's a lot of kind of similarities here. We can talk about chicken or egg type of scenarios between the star formation rate and quasars, but they're kind of all from the same thing. If we have these colliding galaxies, we just have this extra amount of dust that feeds the black hole and feeds the excess star formation. So we can see this this combination of properties here at once.